Welcome. Let's understand the idea of exponential decay. What if we have some value? In this case, let's consider the value of 2, and then we keep multiply by some number between the values of 0 and 1. In this case, I am going to consider the value of 1/2. So now let's take a look at what would happen. So let's get the value of 2, and then let's multiply by 1/2. Then we're going to get the value of 1. And let's do the same. Let's get the value of 1, and then let's multiply by 1/2. Now we're going to get the value of 0.5. And let's do this again. Let's get 0.5, and let's multiply by 1/2. And now we're going to get 0.25, and let's continue doing this. In terms of behavior, when we keep multiplying by 1/2, our values are getting smaller because we have a constant behavior of multiplying by 1/2. We can write an equation for this. The value that we started, it was given. We did not multiply 1/2 to obtain this value. Then we can represent this value as 2 times 1/2 multiply 0 times. The value of 1, it was obtained when we got the value of 2 and we multiply times 1/2 one time. So we can write an expression for this. We can say that the value of 2 is equivalent to 2 times 1/2 raised to the first. We only multiply 1/2 one time. The value of 0.5, it was obtained when we got the value of 2 and we multiply times 1/2 two times. So we can represent this number as 2 times 1/2 raised to the second. The value of 1/2 was multiplied 2 times. The value of 0.25, it was obtained when we got the value of 2 and we multiply 1/2 3 times. So we can represent this value as 2 times 1/2 raised to the third. The value of 1/2 was multiplied 3 times. And we can do the same for the numbers that follow. The next value, it can be represented as 2 times 1/2 raised to the fourth because we multiply the value of 1/2 4 times. The next value, it can be represented as 2 times 1/2 raised to the fifth. We multiply it times 5 times. And the last value, it will be raised to the sixth. When we take a look at all these expressions, notice that we always had 2 times 1/2. The only thing that changed from expression to expression was the value of the exponent. So let's introduce the variable of x to be the placeholder for the different values that we have as an exponent. And now we can come up with an equation that will represent this scenario. Now we will have y equals 2 times 1/2, which is what appears in every single expression. And now for the exponent, let's place the variable of x. It is here where we can place the different values of 1, 2, 3, and so forth. And now we have an equation for this scenario. This is what we define as an exponential function. The variable, it's on the exponent. Let's take a look at the graph of this equation. One thing that we can notice about the graph is that as we keep moving to the right-hand side, the values of y are decreasing. The reason that this occurs, it's because of the number that we keep multiplying. If we were multiplied by 1/2, we were always cutting in half the previous value. And in terms of our equation, that is the base of our exponential. Anytime that we have given any exponential equation, if the base is between 0 and 1, we will have an exponential decay function. Another thing to notice about this graph is the location of the y-intercept. It is occurring at the value of y equals 2. This is the same value that we started in our example, and in addition, in our equation, it is the value that does not have an exponent. So now let's summarize how we can read our equation. The reason why we can say that this is an exponential function, it's because the variable is located on the exponent. If the base of the exponent is some value between 0 and 1, which in this case is 1/2, we are guaranteed to have a function that decreases in value, an exponential decay. And given this exponential decay, the value that does not have an exponent, it will always be the y-intercept of our graph. Now let's take a look at a scenario where we are going to be changing the value of our base. So here we have the same graph as we had in our previous example, where the base was equal to 1/2 and the starting value was equal to 2. What would happen to the behavior of this function as we increase the value of the base? What if we start choosing values that are getting closer to 1? Notice that our exponential decay function, it is looking more like a flat horizontal line. Even though our graph is starting to look like a horizontal line, the value of my y-intercept, it is not changing. It is still 0, 2. But what if we go the other way around? What if we start choosing values of the bases that are closer to 0? It is the opposite. Our exponential decay function, it is looking more vertical. But one thing to notice is that the value of our y-intercept did not change. So let's summarize this. When we are only looking at values of bases between 0 and 1, we are guaranteed to have an exponential decay. But if those values are getting closer to 1, my exponential decay function, it's starting to look more like a flat line, and the other way around, as the value of my bases are closer to 0. My exponential decay is starting to look more like a vertical line. But in both of those cases, we were always decreasing. Hello. If you would like to continue learning about mathematics, you can check out the videos on the left.